Hello, and welcome back to Greg Does Physics. Today, we're going to be doing problem 1.38 in Griffiths E&M. 1.38 asks us to express the unit vectors r hat, theta hat, phi hat in terms of x hat, y hat, z hat. That is, derive equation 64. Check your answers several ways. For example, the dot product of the r hat should equal 1. The dot product of theta hat, phi hat should be 0. Is the cross product of r hat and theta hat, phi hat, etc. Also work out the inverse formulas giving x hat, y hat, z hat in terms of r hat, theta hat, phi hat, and theta and phi. Now this problem, I wouldn't say it's extremely complicated or rigorous or really tests your knowledge of some underlying physics principle. However, I do think it's a solid question in terms of introducing the concept of this spherical system of coordinates. So why don't we get into that? What is that? So we already know of our regular Cartesian coordinate system, x, y, and z. But now we're going to be looking at what's called the spherical coordinate system. And rather than being in terms of x, y, and z, our variables are r, theta, and phi. So let's say we have some point P out here, and we're looking for the coordinates of that point, that displacement. So r would just be the distance from the origin straight to that point. Simple enough. Theta, or the polar angle, is the angle from the z-axis down to the displacement vector for that point here. And then our azimuthal angle, phi, is the angle from the x-axis over to the projection of this displacement vector for p in the xy plane. And so we can see naturally that r would range from 0 out to infinity. Theta, we run from 0 down to pi, and our azimuthal angle will run all the way from 0 to 2 pi back around. If we had theta extend beyond pi to say 2 pi, then of course we'd be double counting points in space, because a point over here, for example, could be accomplished by some value of theta and then just running phi further around, rather than having to run theta all the way around to get that point. Now, that also might lead you to ask the question, why is it that we have theta run from 0 to pi and phi run from 0 to 2 pi? Why not the other way around? Why can't we have theta run from 0 to 2 pi, and then, to avoid double counting points, then we have phi run from 0 to pi? And theoretically, we could do that. It's just sort of standard notation to not do that. But there are good reasons to have it the way we do have it. And one example would be, for example, in spherical coordinates, if you were to take an infinitesimal volume element, in Cartesian coordinates that'd be dx, dy, dz. In spherical coordinates, that would be r squared sine theta dr d theta d phi. But if we allowed our theta to run from 0 all the way to 2 pi, then that sine theta term in the volume element, or also it could pop up in an element of area, could run negative. And of course, having a negative volume is nonsensical physically. So for that reason, we keep theta restricted 0 to pi, and phi runs 0 to 2 pi. Now, the question wants us to manipulate the unit vectors that show the direction of these quantities, r hat, theta hat, and phi hat, much like x hat, y hat, and z hat. But the problem is that in Cartesian coordinates, those unit vectors are constant. X hat is always pointing in this way, y hat is always pointing in that way, and z hat is always pointing in that way. But these unit vectors depend on where you are in space. Because, for example, r hat is always pointing radially outward. So at this point P, it'd be pointing in that direction. But if, say, we had a point over here sitting on the x-axis, now r hat would be in this direction. And likewise, whereas our phi, our theta hat before, was perpendicular to that, facing, going in this direction, now instead it'll be going directly downward, like that. And then our phi hat, whereas before it was pointing around like that, sort of into the board, now instead it's going to be pointing this way. And so you can see how the direction of these unit vectors change with respect to their position. And that's why it's pertinent to get these unit vectors in terms of Cartesian unit vectors, x hat, y hat, and z hat, so that when we're going back and forth between spherical and Cartesian coordinates, we can account for this change. So, to start off, let's recall the how we get the Cartesian coordinates x, y, and z in terms of the spherical coordinates r, theta, and phi. Z is the easiest one to see because clearly, again, if we're revisiting this point P, it's just pretty simple trigonometry. This point P runs back to the z-axis, and so our z-coordinate would just be r times the cosine of the polar angle theta. That would give you your z-coordinate. Likewise, now if you were to take the r sine theta, that would give you the component of this displacement vector in the xy plane. It would give you this right here. And so if we want to get y and x, then all we have to do is, again, using trigonometry, use our phi. And so we can see that r sine theta, if we were to attach sine phi, that would give us our y coordinate. Hence y equals r sine theta sine phi. And then attaching a cosine of phi would give us our x coordinate. Hence x equals r sine theta cosine of phi. All right. So now we've got our Cartesian coordinates in terms of the spherical coordinates. I'm going to start by calculating the r hat direction, and I'll show you a sort of easy way to do it, sort of like tricky, well, a trick sort of to get r hat quickly, but then I'll do it through a more sort of informative method that we'll also use to repeat to calculate theta hat and phi hat. And the easy way to do it is that if we recall our displacement vector r, we can write that as x hat plus y hat plus z hat. Or another way to write it is to write the magnitude of r in the direction r hat. So this is a displacement vector. But then if we were to write these x, y, z coordinates in terms of the polar coordinates, then we get r sine theta cosine phi x hat plus r sine theta sine phi y hat plus r cosine theta z hat. And knowing that this equals r hat, then we could get our r hat just by canceling out these r's. And indeed, you'll see that this is the equation for r hat. Now let's think of another way to calculate this. There are a number of ways that you could calculate r hat, theta hat, and phi hat. You could just use trigonometry for example. I'm gonna do a method that's a little bit more analytically approachable. And so let's say we have a displacement vector, this displacement vector r, and say we wanted to change our r by some amount in the r hat direction. How would we do that? Well, we would say that dr then is equal to d dr like this. We would take, we would look at the rate of change for our position vector with respect to r, and then we would multiply it by whatever amount dr that we're changing it by, and this would give our change in that position vector if we're only doing it in the r hat direction. But knowing that we've written this such that this should only point in the r hat direction, then we can see that this d dr r hat should point, position vector, should point in the r hat direction. And so then if we wanted to get the r hat direction, we would just normalize this result like this. Divide that result by its magnitude. So let's go out and do that. So looking back, I'm gonna sort of erase these a little bit. So let's derive this with respect to r. It would become sine theta cosine phi x hat plus r sine theta sine, plus sine theta sine phi y hat plus cosine theta z hat. And then the magnitude of this would of course just be the square root of the sum of each of these terms squared. So for example, we would have sine squared theta cosine squared phi plus sine squared theta sine squared phi. But that quantity, we can take that sine squared theta out, and we're left with something that looks like this. This is 1, and then we're left with sine squared theta plus cosine squared theta, which again is 1. And so that way we can see that this is already normalized. So we can see again that this is r hat. But look, it's the same thing that we've already derived. So there we go. We have confirmed that that is r hat. Now if we want to get theta hat and phi hat, we can do that in this using the same method. So let's do that. So we derive the position vector with respect to theta, and that would give us r cosine theta cosine phi x hat plus r cosine theta sine phi y hat minus r sine theta z hat. And so then to get the magnitude of this, phi r squared cosine squared theta plus cosine squared phi plus sine squared phi plus r squared sine squared theta. This is again 1, and so then what we're left with is r squared times cosine squared plus sine squared, which is again 1, and so our magnitude squared is r, hence the magnitude is r. So then if we want to get theta hat, we'll just divide this vector by r, since that's the magnitude, and so that gives us cosine theta cosine phi x hat plus r cosine theta sine phi y hat minus, whoops, there shouldn't be an r there, minus sine phi z hat. Alright, so now finally let's get phi hat, and we're gonna again do that in the same way. Differentiate our position vector with respect to phi, and we'll get minus r sine theta sine phi x hat plus r sine theta cosine phi y hat, and there's no phi term in the z hat, so that just goes to 0. Then we want to normalize this. R hat phi squared equals r squared sine squared theta sine squared phi plus cosine squared phi. This is 1, and so our magnitude of this is r sine theta. So then to get phi hat, we just divide this by r sine theta. So minus sine phi x hat plus cosine phi y hat. And if we look back at Griffiths at equation 64, does this match? And that does, and that does, and this does as well. Okay, so we've calculated these unit vectors. Do they make sense? Well, let's try it for example, just by let's look at where I put the unit vectors here. If we were to look at which direction the unit vectors are pointing, sitting on the x-axis, would we get the directions that these are saying? So r hat, for a polar angle of pi over 2 and a azimuthal angle of 0. So azimuthal angle of 0, this goes to 0, and then so this would be 1 times 1, so this would be x hat, and this would be 0, so then we'd have r hat in the x hat direction. That is what we get. Let's look at theta hat. So cosine of theta is going to be 0. Sine of phi is going to be 0, but sine of theta is going to be 1. And so what we get is that here on the x-axis, theta hat is pointing in the negative z hat direction. That makes sense based on what we've drawn. And finally, let's look at phi hat. Again, sine phi is 0, so then we get the y hat, just 1 times y hat. So phi hat is pointing in the y hat direction, and again, that's what we expect. So that's a good little sanity check. Another thing we could look is making sure that these unit vectors form what's called an orthonormal basis. And that basically just means that each of these unit vectors are normalized. They have a magnitude of 1. And that they are orthogonal to each other, or perpendicular to each other at all times, and at all positions. And the way to do that would just be taking dot products of these things with themselves. So if you took the dot product of theta hat with itself, you would get cosine squared theta. You'd take out cosine squared, because it'd be multiplying the magnitude of cosine squared phi plus sine squared phi, which is 1. So you get cosine squared theta plus sine squared theta, which would be 1. So that is a magnitude of 1. You can repeat that for phi hat and r hat. And if you were to take the dot product of any two of these different ones together, for example, if we were going to do r hat dotted with phi hat, then cosine theta would be multiplied by 0. We would get sine theta, sine phi, cosine phi, minus sine theta, sine phi, cosine phi. It would be 0. So they're orthogonal. And you can do that with any of these vectors. I won't delve into how you get orthonormality from taking the dot product, but it just comes naturally from what dot product means geometrically. And then you can take cross products too to make sure that they look how you would expect them to. Griffiths asks you to do, for example, the cross product of r hat and theta hat and check that it equals phi hat. I won't do that. You can do that for yourself though, but it would work out in that way. So all that is to say is that we have got our equations for r hat, theta hat, phi hat, and we're confident in our answers, and they match up with what Griffiths derived. So now what we want to do is we want to work backwards in a way. We want to get x hat, y hat, and z hat in terms of r hat, y hat, and z hat. R hat, theta hat, and phi hat, my bad. So I'm going to now erase this, and we'll be right back. Welcome back. So I have gotten the equations for r hat, theta hat, and phi hat that we just solved for written out now, and our goal is going to be calculating x hat, y hat, and z hat in terms of the unit vectors for spherical coordinates, r hat, theta hat, and phi hat. And really all that's going to be is algebraically moving these equations around. For example, let's look at what would happen if we were to... How would we get this z hat isolated? Well, we could do sine theta r hat, which equals sine squared theta cosine phi x hat plus sine squared theta sine phi y hat plus cosine theta sine theta z hat. And then we could also multiply this one by theta, so cosine theta hat equals cosine squared theta cosine phi x hat plus cosine squared theta sine phi y hat minus cosine theta sine phi z hat. Interesting. These two look pretty similarly. So if we were to say add these two up, sine theta r hat plus cosine theta hat, we would get sine squared theta plus cosine squared theta, that quantity multiplied by cosine phi x hat, so we could just write cosine phi x hat since that becomes 1. Same thing over here, we can write plus sine phi y hat, and then these z hat terms cancel out. So we get sine theta r hat plus cosine theta theta hat equals cosine phi x hat plus sine phi y hat. But we'll also notice that this part looks sort of similar to our equation for phi hat. Phi hat equals minus sine theta x hat plus cosine phi y hat. We know that sine squared x plus cosine squared x equals 1. And we're going to use that fact to try and isolate these x hats and y hats. So, for example, we could multiply this out by cosine phi. So we get sine theta cosine phi r hat plus cosine theta cosine phi theta hat. And then how about we subtract a sine phi phi hat, and what would that give us? That would give us cosine squared phi plus sine squared phi x hat plus sine phi cosine phi minus sine phi cosine phi y hat. That's 0, that's 1, and so this is our equation for x hat. Now y hat, we basically just do the opposite and we add. So we would multiply this top one by sine phi, so sine theta sine phi r hat plus cosine theta sine phi theta hat, and add cosine phi times phi hat, and that will give us cosine phi sine phi minus cosine phi sine phi x hat plus sine squared phi plus cosine squared phi y hat goes to 1, goes to 0. This is just y hat. So now our final task is going to be to calculate z hat. And let's look back up here, specifically at r hat and theta hat, since they have z hat terms. Again, if we think of the whole cosine squared plus sine squared equals 1, then we could see that we could just multiply theta hat by negative sine and r hat by cosine of theta, and that would add up so that we just get a z hat term. So let's do that. So we would say cosine theta r hat minus sine theta theta hat equals, start with the x hat terms, we get sine theta cosine phi minus sine theta cosine phi plus y hat. That would be sine cosine sine cosine sine minus sine theta cosine theta sine phi, and then finally plus z hat cosine squared theta plus sine squared theta that of course is 1, and you can obviously see that this is 0, and this is 0, i.e. this is z hat. Alright, and there we go. So we've got our x hats, y hats, and z hats in terms of r hat, phi hat, theta, and phi. And again, you could check that these vectors are, these unit vectors, work as you expect. You could take the dot product of any of them with themselves and you would get 1. You could take the dot product of any unit vector with a different one and you would get 0. The cross products work out as you would expect. Basically, these are right. These make sense. And that's pretty much all. I hope this helped. Like I said, it's not the most, crazy, delving into big physical mysteries. This problem sort of just uses geometry and a little bit of common sense and a lot of algebra. But it works out some interesting results, and it's good as an introduction to spherical coordinates. And that'll be all for today, so thank you.